Hello everyone and welcome to today's webinar, which is brought to you by Bettersize Instruments in partnership with AZO Network. Today's webinar is titled From Powder to Power, Advancing Cement Research with Particle Analysis. A big thank you to the team at Bettersize Instruments for making this event possible. We're going to get started in a couple of minutes, but before we do, let me introduce today's wonderful speakers and explain a little bit about the format for today's webinar. Today's webinar will run as two parts, a presentation and an audience Q&A session. The first of today's fantastic speakers, and getting us started in just a moment, will be Dr. Gong. Dr. Gong is an assistant professor of civil and environmental engineering at Rice University. His research lies at the intersection of materials science, civil engineering, environmental sustainability, and data science. He leads the Sustainable Infrastructure Materials Group, which focuses on addressing fundamental challenges in building materials, particularly emerging cement and concrete technologies, with the goal of advancing a more durable, sustainable, and resilient built environment. Dr. Gong will be joined by Weichen Gan, an application scientist at Bettersize Instruments. He earned a master's degree in materials science and engineering from the University of Florida and received his bachelor's degree in materials science and engineering from Harbin Institute of Technology. Since joining Bettersize, Weichen has been focusing on the characterization of the physical properties of inorganic materials and helps provide relevant solutions. A big welcome to you both today. Before getting started, we have a few points about how to get the most out of your experience today. Firstly, the event is being recorded and we will share the on-demand link with you within the next 24 hours. So, if you enjoy what you see or you have a colleague or peer who may benefit from seeing the content as well, please do share that recording with them when you get that email. Refreshing your browser normally resolves technical issues. But if this doesn't work, send a message using the Q&A box and our back-end team will get you back up and running as soon as possible. As I mentioned, there will be a Q&A session following the presentation, so please send those questions in at any time and we'll get to as many of them as possible following the presentation. A quick note that if you are watching this back on demand, then you can still ask your questions, but you will receive an answer via email. Now, let's get things started with the presentation. Dr. Gong, over to you.
All right. Thanks for the introduction, and thanks for Bettersize for organizing this webinar, and thank you all for joining today's seminar. The title of my talk is also a brief description of the vision of my research group at Rice University, a material science-based and data-driven approach towards sustainable and durable infrastructure. So here is the outline of my talk today, which consists of 3 parts. Now, in the first part, I will briefly talk about the big picture of our research, and then I will take you through some of my recent work, specifically in 2 areas. Now, one of them is on the use of AI to optimize concrete mixes. Now, the second one aims to establish the important composition, structure, and reactivity relationship for different alkaline solid waste, so that we can better utilize them for concrete production. Now let's get started. So the goal of our research is to help tackle what I believe is one of the greatest societal challenge of the 21st century. That is how to meet our society's growing demands for buildings, resources, and energy, while at the same time minimizing the associated impact of this on our environment and climate. Now, resolving these challenges requires collective efforts and innovative solutions from many different sectors, now especially the building infrastructure sector, because the building infrastructure sector alone accounts for about 40% of the global greenhouse gas emission and 40% of the global energy consumption. Now, according to a recent study, this building infrastructure sector either directly or indirectly influences all the 17 Sustainable Development Goals identified by the United Nations. Now, within the building infrastructure sector, the sustainability of infrastructure materials, in particular cement, concrete, and steel, have a critical role to play in helping us achieving these goals. Now, take Portland cement, for example, which is an amazing powder that has been used almost everywhere, now essentially forming the backbone of modern infrastructure. However, the production of this powder alone accounts for about 8% of global carbon emission, 2 to 3% of the global energy consumption, largely because of this calcination of limestone at a temperature of 1450 degrees Celsius. Now, on a business as usual scenario, these figures are projected to increase over the next 3 decades, because the global cement demand has been projected to increase by 20 to 30% over the next 30 years. Therefore, there is a pressing need to decarbonize cement and concrete industry. While this is a challenge, a significant challenge, while this is a significant challenge due to its vast scale, it also presents enormous opportunity. To date, many different strategies are being actively explored across academic and industry all around the world. Now, this includes developments of more sustainable, cement and concrete materials, including blended cement and low CO2 cement technologies in the materials production stage. This includes the design optimization stage, where we improve the mix design or binder chemistry so as to improve the performance. This also includes the improve of materials efficiency through the use of advanced manufacturing technologies, so on and so forth. And my research to date has mainly focused on or contributed to the first two stages, in the materials production stage and the design optimization stage. Now, specifically, my group at RISE focused on the most critical material science problems related to emerging low CO2 cement technologies. Now, especially those related to or incorporated with waste recycling and design optimization. Now, our goal is to fundamentally improve the sustainability and durability of infrastructure materials. Now, to achieve this goal, we combine a top-down approach, a top-down data-driven approach, and a bottom-up material science approach. While this top-down approach helps us identify important problems to focus on, this bottom-up approach then aims to fundamentally solve the problems from atomic scale. Next, I'm going to share one example in each of these two directions that I mentioned to you, just to give you a flavor of the type of research we do in my group. Now, the first one is the use of AI to optimize concrete mixes. The work I'm going to share is from my postdoc at MIT with Professor Elsa Olivetti in collaboration with the IBM Machine Learning Lab. Now, if you are interested in more details of this study, please feel free to check out this paper. So this study is motivated by the amazing abilities of AI to capture the complex correlations between concrete composition and the final engineering property. Now, compared with the current prescriptive and try-error approach that are adopted by the industry, AI approach offers many advantages, and one of them being the ability to generate an optimal mix design in a matter of seconds or minutes. Now, the problem is, how much do we trust them, right? How much do we trust the AI optimized mix design? And hopefully, these studies helped increase this confidence, or at least help revealing this significant potential. Now, over the past 20 years, there has been increasing number of papers in the application of AI in concrete science, as you can see in this figure. Many of them focused on concrete strength prediction, and a few of them on mix optimization as well. So most of these studies used small and simple data sets, as you can see in this figure, most typically less than 1,000 data points. However, modern concrete mixes are highly complex. As such, they often require larger or more complex datasets to develop more reliable and robust AI models to achieve reliable prediction. In order to design a realistic concrete mix the industry can use, the model needs to be exposed to actual industry data. So we were very fortunate to obtain a large industry dataset from a concrete producer. Now here is a summary of some statistics of the dataset we have. And overall, we used 12 mixed proportions along with the water to cement ratio. So in total, 13 features to build AI models to predict concrete strengths. Now here is an overview of our computational framework, which consists of three modules: a strength prediction modular, an optimization modular, and an objective modular. Now the strength prediction modulus allows us to estimate the concrete strengths as a function of the mixed proportion, while this objective modulus allows us to estimate the cost and climate impacts a mixed design has. And this optimization modulus in the middle generate mixed design that minimize the cost and the climate impact through this optimization, through this objective modulus, while at the same time make sure they're meeting the strength targets according to the strength prediction modular. Now, if you're interested in more details, feel free to check out the papers. Now, let's look at some results. Now, firstly, the performance of the strength prediction modulus. So we have compared the performance of three different AI algorithms: the Gaussian process regression, random forest, and artificial neural network. Now, the horizontal axis in this figure are measured strengths in PSI, and the vertical axis are predicted strengths. And as you can see that all our models give very high predictive accuracy with R-square values close to 0.9, which is pretty good for such a complex industry dataset. Now let's look at the optimization results. On the left side of this slide shows the cost of the optimized mixes, which are given by the triangles and the squares at the bottom, as you can see, when optimizing cost. And when compared with the industry mix, the cost of the industry mix design, which are given by the blue circles, right? Each circle is a mixed design. We can see on average, the AI optimized mixes are about 20 to 30% cheaper than industry mix design. Now, on the right-hand side is a figure for optimizing climate impact, which shows that the AI optimized mixes on averages has about 60% lower climate impact compared with the industry mixes. Now, based on this framework, we can also do bi-objective optimization using a weighted sum method to consider both the cost and climate impact into the equation. Now, the result is shown in this figure, where this connected line, these solid connected lines in the figure are the Pareto fronts for different target strengths. Now, which shows essentially the trade-off between the cost and climate impact. But we can clearly see or clearly identify there are some optimum mixes at the bottom left corner, right? That are both low in cost and climate impact. Now, in summary, this study has shown that AI-driven mix optimization has significant potential to reduce both the cost and carbon emissions of concrete mix design. However, to fully unlock its potential, there is more work needed that we are currently working on. Now, this includes experimentally validate the AI optimized mixes. This also includes to incorporate more performance metrics into the framework. For example, slump and air content data, which are also important performance metrics. This also includes incorporate more domain knowledge into the model so as to further enhance the reliability and robustness. Now, this includes particle size, distribution, and density information of the raw material. Now, let's now move on to this third part, which focuses on understanding the atomic control of reactivity for different alkaline solid waste that can be used to enhance the sustainability and performance of concrete. Now, this part is based on a collection of my recent work, as shown here. If you're interested, feel free to check out these publications. Now, let's start it by motivating this part a little bit. Now, what I'm going to focus on is three industrial waste materials, which is blast furnace slag, byproducts from steel production, coal fly ash, byproducts from coal-fired power plants, and volcanic ash from volcanic activities, which are all very fine powders that has been widely researched in the community as something we can use to produce sustainable cements. Now, currently, about 50% of the coal fly ash that generated annually around the world is actually used in concrete production. So that is about 350 million tons per year. So the associated environmental benefits of this utilization is equivalent to removing 50 million passenger cars from the roads for 1 year. Now think about it. If we could utilize the remaining 50% of this annually landfill fly ash, or those fly ash stockpiled in the landfill from the previous decades, there are in the world there are currently about 2 gigatons of landfills stockpiled fly ash, or the more abundant volcanic ashes. The potential environmental benefits are huge. Now, more importantly, in addition to these three examples I'm giving, there are many other alternative waste powders that can be utilized for concrete production. Now, overall, these low CO2 waste materials can be utilized for concrete productions, many in two different ways. On the one hand, as you can see on the top, we can utilize them as a supplementary cementitious material to partially replace Portland cement so that we can lower its carbon emission. On the other hand, we could just mix these waste powders with an alkaline solution to make the so-called alkaline activating material, which is an important class of low CO2 cement binder that has been researched all around the world. However, one major challenge is for recycling these waste materials through these two applications. Now, especially in the alkaline activated material system, which is essentially based on 100% of this waste, is the inherent chemical variability of this waste, as illustrated in this ternary composition diagram. So this inherent variability leads to very different reactivity, which then make the property of the final products, especially AAM, less predictable. And obviously, this is undesirable for the engineering applications, right? As an engineer, we want to be able to predict the materials we use to build and construct. Now, to fundamentally solve this problem, the best strategy from a material science perspective is to fundamentally establish the relationship between composition, atomic structure, and property, as you can see in the left figure. However, these relationships are not yet well understood. Now, most of the existing studies in the literature or in standards focused on using empirical compositional parameters without any structure information, which we know structure information has a large impact on the properties of these waste materials. And because of that, the reliability and transferability of these compositional parameters are often limited. And therefore, the reliability and transferability of these compositional parameters are often limited. Therefore, the goal of this collection of work is to help us generate the detailed atomic structure information to complete this triangle. Now, the challenge now here is, how do we obtain detailed structure information on these low CO2 waste material? Because the main reactive components in these materials are highly amorphous, meaning that the arrangements of atoms in these materials are highly disordered. So this is different from a crystalline material where the atoms are highly ordered. In that case, we can use X-ray diffraction to determine the atomic structure. But for amorphous materials, in the case of these waste materials, their structure cannot be determined using conventional X-ray diffraction experiments. But for this purpose, atomistic simulation combined with advanced X-ray and neutron scattering is a promising solution, which is what I'm going to show you today. Now, specifically, this collection of work aims to address a series of questions, including these two. Now, the first one is, can we generate detailed and reasonable atomic structure for this waste material composition, amorphous material composition, using atomic simulation? Now, the second question is, once we have the atomic structures generated, can we then develop or identify structure fingerprints or descriptors that allows us to predict the relative reactivities of these different waste materials so that we can better predict the engineering properties of the final products? Now, to generate the detailed atomic structure of these amorphous materials, I used molecular dynamic simulation following a simulated melting and quenching process as illustrated in this figure. Now, you can find more details in the publication and interest if you are interested. In the interest of time, I won't get into details. Now, to verify whether the structures we generated using this computational method are reasonable or not, we have collected some X-ray and neutron total scattering data, which can be directly compared with our simulation data. Now, let's check out some results. Now, firstly, here is the typical atomic structure generated for a typical slag, which is industrial byproducts from steel production. And based on these structures, I have calculated the X-ray and neutron scattering data and compared them with the corresponding experimental data. As you can see, there are good agreements for both the X-ray total scattering data on the left and neutron scattering data on the right. I've also calculated the atomic bond distances within the materials based on the atomic structure and compared them with my own experimental data as well as literature data as summarized in the table, which shows that the differences are smaller than 2%. Another comparisons we did is the coordination number, which is defined as the number of oxygens in the nearest neighbor shell of a metal cadence as illustrated in the top figure. And the comparison shows, as summarized in the bottom table, is that they also agree reasonably well with the literature data on similar materials. Therefore, all these results shows that reasonable atomic structure indeed can be generated using these atomic scale simulations. Now let's get to the second questions, right? Now we have the atomic structure, reasonable atomic structure generated. Can we develop novel structure descriptors that allows us to predict the relative reactivities of these different raw material? We have developed several different structure descriptors as listed here, right? But in this talk, I'm going to focus on the first one, which is the average metal oxygen dissociation energy, AMOD. Now, AMOD parameter is calculated using this following equation as illustrated here. Now, you can understand this equation in this way. Say, if we want to dissolve, for example, aluminum from the waste material, right? Aluminum oxide from the waste material. So we need to break all the aluminum oxygen bonds. Now, this BS, bond strength parameter, essentially tells us the energy that is required to break a single aluminum oxygen bond. And this CN coordination number, CN, tells us how many of these aluminum oxygen bonds we need to break in order for a single aluminum atoms to dissolve from the structure. And these N parameters at the bottom essentially tells us the amount of aluminum atoms we have in the system. So overall, this equation tells us the average energy that is required to break all the metal oxygen bonds in the material. So based on this definition, right, for a material with a lower AMOD value, it means that on average it takes less energy or less effort to break all the metal oxygen bonds or to dissolve the whole material to allow it to participate in reaction. And therefore, it's going to be more reactive, right? Now let's look at the performance of these amode parameters in predicting the relative reactivity of calcium aluminum silicate glasses in alkaline environments. Now, these calcium aluminum silicate glass are designed to simulate different slag and fly ash. Fly ash are industrial byproducts from coal-fired power plants. Now, we can clearly see an inverse correlations between these amode parameters that we get from the atomistic simulation and the extent of reaction from quantitative X-ray diffraction. Right? So this trend is consistent with expectation because a lower amode value, a sample with a lower amode value, it means it takes less effort to dissolve the whole sample to allow it to participate in reaction, right? And therefore, the higher extent of reaction at a given time, right? So this kind of inverse correlations is consistent with our expectation. We then applied it to volcanic ashes, which has more complex chemical composition as illustrated in this table. And now the chemical composition of these different volcanic ashes varies considerably. And because of this chemical variability, the log dissolution rates of these different samples at both low and pH solutions varies by over 2 orders of magnitude, as you can see on the right-hand column, on the columns on the right-hand side. Now let's check out whether our amode parameters can capture this significant difference in dissolution rates. Now, here is the results. The lower the amode values means lower energy required to break the sample, and therefore higher reactivity, and therefore higher dissolution rates. And yes, they are captured, right? So we get these inverse correlations. Now, in conclusion, we showed that reasonable atomic structures can indeed be generated for a wide range of amorphous aluminum silicate-rich waste that are used for concrete productions. Now, based on the structure generated, we showed that it is possible to develop physics-based structure descriptors, and we showed amode as an example here. That can help us capture the relative reactivities of these different materials. So based on these results, we actually later on extended to develop a modified amode parameters that can perform as good as the original amode, but then this can be directly estimated using their chemical composition without computationally expensive atomic simulation. So this can be potentially developed into a fast screen methods for these waste materials for industry application. So at the same time, there are a number of limitations for this method that needs to be considered. We are currently working on resolving these limitations, and one of them is that the reactivity of these raw materials is actually highly complex. Right? In addition to the composition and structure factors that we considered here, the reactivity also depends on temperature, pH, as well as the particle size distribution. Now, for more information on the discussion of these limitations, please feel free to check out our paper. With that, thank you for your attention. I will now hand it over to Weichen.
Thank you, Daniel, and thank you, Dr. Gong, for guiding us through such a creative and informative journey. Hello, everyone. My name is Weichen Gan, an application scientist of Bettersize Inc. For the following part, let's explore why some particle-related characteristics, like particle size, are key parameters for cements and how we measure them. Through the following introduction and case studies, I will demonstrate practical measurement techniques and their impact on advanced cement research, production, and quality control. Let me briefly introduce the topics we will be examining today. First of all, we will cover particle size and the key solution for particle size analysis, the laser diffraction method. Then, we will introduce the Bettersize solution for testing cements with laser diffraction technology. After that, we will introduce different definitions of density and provide a reliable technology for density measurement, gas picnometry. To refresh our memory, the size of cement has long been related to its performance, thanks to the hydration and hardening process. Just like Dr. Gong mentioned, PSD control plays an important role in the entire cycle from research and development to actual large-scale production. For R&D process, we are clear that different materials play different roles in the cement, and particles of different materials are designed to varied sizes, such as the ordinary Portland cement, the OPC from Dr. Gong's speech, and sustainable counterparts of OPC like fly ashes, steel slags, etc. A balanced blend of not only the material but also the particle size distribution, PSD, optimizes cement's practical performance. Also, since PSD is the key to performance, consistent particle size distribution also be an important guarantee for turning design into real value. We all agree PSD is a key factor, but how can we control it? In the cement industry, the most widely accepted method is to control grinding processes. The grinding process is like a subtle balance of energy input and product outcome. When every second counts for the grinding processes, unsaturated grinding like test 1 and overgrinding like test 3 are both a waste of materials, energy, and time. Moreover, when the response is slow or not accurate enough, a large overgrinding insurance is required to ensure particles are well ground. That would be another hidden cost of energy. Let us imagine, what if we can make particle size measurements at higher efficiency and accuracy? First of all, adjustments of grinding processes can be made at a faster pace. In this way, waste from product failures can be avoided. Also, higher measurement accuracy can help us reduce the overgrinding insurance since we can be more confident in the measurement results. So, in return, the energy costs are also reduced. The result is clear. An accurate and efficient PSD measurement helps reduce the energy cost on every aspect. In a larger picture, the energy used to drive the grinding equipment can also be saved, which can reduce negative environmental impacts such as greenhouse gases granted during production. As we discussed, the pursuit of better accuracy and efficiency is an eternal topic. So, what are mainstream methods today? Traditional methods like sieving and air permeability has long been an important part of the cement production process. Sieving provides a rough PSD while air permeability focuses on the overall average of specific surface area (SSA). However, the sieving method presents some challenges when dealing with fine particles, around 40 microns and below, and the resolution and accuracy of sieving result can be limited. As the only output of the air permeability method, the blame value brings some blind spots to quality judgment. Two cement samples can have identical blame values but exhibit divergent performance in concrete. That's where the laser diffraction (LD) method comes in. This advanced particle size analysis method allows us to precisely and quickly measure particle size distribution, ensuring consistent product quality and minimizing these frustrating issues. Like all the historical methods, LD ensures a systematic and reliable testing process. Moreover, it delivers high-resolution PSD curves with advanced efficiency. This allows more precise quality control and optimization of cements as we discussed. This slide illustrates the principle of light diffraction. This method is also known as light scattering since it utilizes the scattering of light which occurs when light interacts with particles. As shown on the left, when light shines on a particle, light scatters. Scattering is a combination of four phenomena: reflection, attenuation, refraction, and diffraction. Diffracted light will project a pattern on a screen in the form of a series of concentric circles of varying intensity. This pattern is called the Airy pattern. If we fix the wavelength of the light, the distance between the particle and the screen, the Airy patterns will vary systematically with particle size, as shown in the picture of the large particle and small particle cases. One thing that needs to be mentioned is, in the real world, particles of mixed size will form a mixed pattern, as shown in the multiple sizes imaging. On our right is a structure of a typical laser diffraction particle sizer. It is made up of a sample feeding and dispersing system, a measurement system. The measurement includes collection process of the scattering spectrum and the analysis of the spectrum. The result would be in the form of particle size distribution, contents of particles in a specific particle size range. In general, laser diffraction technology provides a wide dynamic range, which means it is appropriate for a range of applications. As we know, most of the cement particles, no matter it is clinker, gypsum, or steel slags, are in micron range. So, the laser diffraction method works perfectly in that range. Meanwhile, the LD test efficiently is good. Usually, 10 seconds would be enough for a single testing process. That makes it possible to monitor particle size changes and have some valuable time for taking action. Also, the results come with good quality. A large amount of particles can be measured with a single test, thus ensuring a good representativeness of results. We have seen how the laser diffraction method has become an important part of the cement industry and how an LD analyzer works. Now let's discover Bettersize LD test solution for cement particles. We are thrilled to introduce the Bettersize S3 Plus particle size and shape analyzer. It is a two-in-one system combining LD technology with image analysis technology. Thus, we can utilize both methods to best understand the size and also shape distribution of particles. For the LD part, the Bettersizer S3 Plus is equipped with a Bettersize patented dual lens and oblique incidence Deloy system to ensure the accuracy of measurements, even for the finest particles down to 0.01 microns. For the image analysis part, the Bettersizer S3 Plus has a dual camera system to rapidly and accurately capture flowing particles. How do we make measurements of shape of micron-sized particles? The answer lies in the image analysis technology. The working process of the image particle size and shape analyzers is to take a photo of the particles and then analyze the particle size and shape with that photo. To clearly observing the particles without distortion, usually people will use an optical microscope or something like a lens to magnify particle images. With each particle image, we can associate several distinct attributes to describe important aspects of the particle, such as circularity, how round the particle is, and the aspect ratio, comparing the difference between particle length and width. As mentioned earlier, the Bettersizer S3 Plus combines laser diffraction and dynamic image analysis in one instrument. Thus, it can measure the size and shape of cement particles from 0.01 micron to 3,500 microns. Benefited from image analysis, it has exceptional sensitivity for oversized particles. With Bettersize's patented Deloy system, the Bettersizer S3 Plus also expanded the lower limit of ultrafine particles detection. the unsurpassed solution and resolution and its sensitivity for either ultrafine particles or oversized particles make it the best powerful size and shape analyzer for enthusiastic researchers who conduct top scientific research. To help better utilize the unique design of Bettersize S3 Plus and to achieve the best performance, to do the measurements more easily, we provided two dispersion units and one optional auto sampler. If the particles are insoluble in water and come in large quantities, such as gypsum or raw limestone powders, then BT803 can be the ideal choice. It is a fully automated dispersion module with automated test functions. Also, it is compatible with ethanol and isopropanol alcohol, making it a good choice for semi-finished or finished cement products that may undergo particle size changes in water. As for samples dispersed in organic solvents with or smaller quantities, there is BT80N works perfectly in this scenario. To make the size and shape measurement of suspensions easier, the BT860 auto sampler is here to help. It can hold up to 60 samples and only one click is needed to do those all 60 measurements. Here is a real-world demonstration of how the Bettersizer S3 Plus helps with cement R&D and quality control. Let's focus on the graph on the right. We will start with a single, consistent base of ordinary Portland cement, OPC, and then created three distinct samples by adding different ratios of fly ash, 50%, 30%, and 15%. The Bettersizer S3 Plus easily resolves these three separate and distinct particle size distribution curves, one for each mix ratio. This is a direct testament to the instrument's incredible sensitivity. It precisely captures the minimal PSD changes that occur when you alter the composition of your product, even by a relatively small amount like the difference between 15 and 30% samples. Furthermore, the clarity and definition of these peaks demonstrate the system's accuracy and repeatability. Instead of a vague chain, you will see a precise quantitative fingerprint of each specific plant. This allows you to confidently compare production batches to your ideal fineness parameters and maintain tight control over product quality. While the standard wet method is precise, the dry method on our Bettersize 2600 offers key advantages for quality control. The wet method of Bettersizer S3 Plus uses a liquid medium like ethanol and processes like ultrasonication. It is incredibly precise and available on all our Bettersizer models. On our right, we have dry dispersion method, which is a key feature of our Bettersizer 2600 model. Instead of liquid, it uses compressed air to disperse the powder. The waiting time for cleaning the whole system between the tests is significantly shorter in the dry dispersion methods, around 20 seconds. This dramatically increases your sample throughput, allowing for faster feedback on the product line. So, the choice is about having the right tool for the right job. For detailed analysis, use the wet method. For fast, high-volume quality control, the dry method is your solution for speed and more representative results. Among definitions of density of powder materials, true density is the density of the solid particle itself, with all the pores and air spaces excluded. For cement, we can state that its true density is effectively equal to its skeletal density, because unhydrated cement particles are generally non-porous and free of any closed internal holes. This allows us to confidently benchmark the value of a typical OPC between 3.1 and 3.25 grams per centimeter cubed. The true density or skeleton density measurement is critical for cements for three reasons. It ensures accurate mix design when converting mass to volume. It impacts performance as denser particles lead to strong concrete. It's vital for creating reliable blended cements. In short, knowing the true density is essential for ensuring accuracy and predictability in the cement final product. Now that we know why true density is important, let's look at the best way to measure it. The traditional Le Chatelier flask method on the left is slow, taking up an hour per sample. It's a completely manual process that uses hazardous, flammable liquids which introduces safety concerns and creates expensive waste. In contrast, gas picnometry, or gas displacement method shown on the right, is a major leap forward. The measurement can be done automatically and incredibly fast, giving you a highly accurate results in just 2 to 3 minutes. Critically, it is orders of magnitude more reliable. By using a safe, inert gas, it completely eliminates all the issues of the older method. There are no clogging problems, no odors, and no environmental waste. The choice is clear. For fast, precise, and safe density measurement, the gas displacement method is the modern standard. So, how does a gas picnometer measure density so accurately? The process is clever and is governed by a classic physics principle called Boyle's law, which relates pressure and the volume. Simply put, Boyle's law states that if you squeeze a gas into a smaller volume, its pressure increases. If you let it expand into a larger volume, its pressure decreases. A picnometer uses this exact principle into two simple stages. First stage, the instrument needs a baseline. Put the weighted sample inside the sample chamber, and then the instrument will fill the sample chamber with inert gas like helium to a set pressure P1. Then, the expansion valve to a second chamber opens, allowing the gas to expand. The transducer will precisely measure the new lower pressure P2. As the equation shows, the volume of samples V can be calculated based on the sample chamber volume VSC, two pressures values P1 and P2, and the reference chamber volume VRC. The chamber volume and P1 are previously input into the software as the pressure transducer reads out P2 accurately. The sample volume can be calculated with incredible precision. Once the volume is known, the instrument simply takes the previously entered mass and calculated the true density, mass divided by volume. At Bettersize, our mission is to provide best-in-class analytical instruments for material characterization, comprehensive solutions, and exceptional customer service. These are just a few of the many successful stories we have seen with Bettersize products. Leading brands and research institutes in the cement industry rely on Bettersize products for their particle characterization needs, from optimizing cement formulations and producing, just like the case study we saw earlier, to ensuring the precise particle size of critical additional materials in cements. And the list continues to grow. We are proud to partner with companies and institutes that are pushing the boundaries of innovation, and we are committed to providing them with the tools they need to succeed. To wrap things up, let's review the key takeaways from our discussion today. We started with the critical importance of the particle size distribution for cement quality. We showed how our Bettersizer S3 Plus which is flexible wet and dry dispersion, provides the sensitive and accurate results needed for both R&D and QC. Then, we explored true density as another cornerstone of cement quality. We highlighted how our Betterpix 380 uses the modern gas displacement method to deliver fast, safe, and extremely precise measurements, making it the ideal replacement for outdated techniques. Ultimately, just like the house on the right, both particle size and true density are the foundation for your final product. Our goal at Bettersize is to provide you with the robust, reliable, and modern tools you need to build better and more consistent cement. Thank you for listening. If you have any questions, we will see you on the live Q&A part. See you.
Hi there, everyone. We will be starting the Q&A very soon. Before we do, we will be starting some polling, so please do answer the polling now. You should see the poll. While you're answering the poll, we will start the Q&A. We've got a couple of questions that have already come in. So our first question is for Dr. Gong. Welcome to you both, firstly. The question is, you mentioned particle size in your slides, but didn't elaborate on it. Could you share more about how particle size affects each of your studies?
Of course. Thank you for the question. So that's a great question. Particle size distribution is important factors in our research. So it's actually one of the key properties for the raw materials, either OPC or these different waste materials that we use to make cements and concrete more sustainable. Is a key raw material property that can strongly influence the engineering performance of the final products. Now, the basic idea is that smaller particles, right? So they have more surface area, right? Finer particles, more surface area, which means they can react more quickly, more reaction sites, and faster reaction then impact not only the early edge property, but also workability, setting time, and also the long-term strength development and durability. So this is why in the industry, particle size are usually carefully monitored. Right? In our AI study specifically, blended cements and concrete is from the industry data set. So we didn't include particle size in our model, not because we have it, but we didn't use it, but because in the data set we have doesn't have that information in the time. But that's something we hope to incorporate in the future if it becomes available. Now, for the second part of our research, which looks into this, reactivity of different samples. So we actually normalize the reactivity measurements by the total surface area, which is directly influenced or controlled by particle size distribution. So that way, after normalization, we can make a fair comparison across different samples with different particle size.
Thank you. And our next question is for Wei Chen. How can I deal with the waste for a Bettersizer S3 plus test?
Thank you. So let's see. Yeah. So this is also a very practical question. So we all understand the cement particles may hydrate in water. So compared with the Bettersizer S3 Plus in the other research area or application field, when using Bettersizer S3 Plus to measure particle size and shape, we may need to disperse cement samples in ethanol or isopropanol alcohol, like IPA. So in this case, we can use an alcohol recovery unit, an ARU, or a similar solvent purifying and recovering system for recycling the solvents, I mean the ethanol and IPA. So the ARU system can filter out cement particles suspended in ethanol or IPA. So the dispersion medium were recovered in that way, and thus costs were reduced. And you can later decide how to deal with cements in the filter.
Thank you. And our next question is for Dr. Gong. What do you see as the biggest challenges ahead for AI-driven concrete design?
Thanks for the question. That's a great one again. And I think the biggest challenge or before I say that, I hope that my study has give you a flavor the potential of AI-driven modeling or AI-driven concrete mix design. I think the biggest challenge is for this, on one hand, is data. Right? So we need to have high quality and diverse data to train reliable models. But this kind of data, especially from industry, is often hard to get. So if you have access to any cement and concrete data and are open to share, we'd love to connect and collaborate. Feel free to reach out. Now, the second biggest challenge, I think, is trust. Like, how much do we actually trust these AI, like predictions from AI model, right, in real world applications? So that means we need to keep improving the accuracy, the reliability, the interpretability and transferability of these AI models. Now, one way to do that is by teaching these models all these fundamental material science, cement chemistry knowledge. But that's not easy. Right? Cement chemistry itself is incredibly complex. And that's where my group is really focused on, combining domain knowledge and AI to make these models more, smarter, more trustworthy, and so that eventually we can deploy it for industry application.
Thank you. And our next question is for Weichen. What is the typical amount of cement used for one gas pinkometer test?
Yeah, thank you. So yeah, this is also a very practical question. So and just like Dr. Gong said, we should to connect the theoretical stuff to the real world like practical thing. So it depends. Let's back to the typical amount of cement using gas picnometry test. It usually depends on two aspects. So the first one will be the original sample amount. We believe that during the actual production, tons of cements are going to be produced every day. In this case, about 5 to 100 grams of cement can be sufficient for one single test, since we have like a lot of cements. However, for researchers, just like Dr. Gon and his fellow researchers, the original sample amount differs from like kilograms to tens of grams. So in this case, the sample volume can also be reduced to 5 to 10 grams. So on the other side, the instrument sample chamber volume is another key aspect that we should consider. As we showed during the second speech, in the gas picnometer, the sample is held in a sample chamber. So the sample should be at an appropriate volume as much as occupying a sufficient space, but not overflowing the chamber. The BetterPick provides three choices for sample cup. Again, it is 10, 35, and 100 milliliters, which in turn covers the range of 5 to 60 grams for the cements. Additionally, as we mentioned during the speech, the BetterPick is equipped with 316 stainless steel sample cups, so it can ensure confidence in its durability when testing cement samples for a longer period, like days or months.
Thank you. That's all the time we've got for our Q&A today. But if you do have any questions, or if you're watching this back on demand, then still do send those questions in and we'll answer them via email. That's the end of our webinar today. We're going to leave you, but we're going to leave the webinar running for a couple more minutes to leave you time to download the handouts in the handouts section. So yeah, thank you everyone for attending. We'll see you next time.